这样子。然后你把它竖，然后你再打一个折，它对应该
对，应该是要下载，要下载什么的。
我是先把它对角化了。
对，对角化。
这角化咱们就相当于重新全部改，就相当于没问题。
当然有问题，当然有问题。因为我觉得要处理的是优的问题，但是这里是脆的，你写。看我的3号本。
Okay, hello. So we're advancing the end. Some of you might have seen I've uploaded previous tests to Moodle, so I recommend you go over them and solve them. The test 2 years ago was in Hebrew, but you can find my handwritten English translation. I hope it's readable. But last year's test was in English as well, so you also have typed questions. I recommend you solve them as soon as possible and stop delaying your homework, because I mean that'll make your life easier. And of course, this year you should expect a very similar test in difficulty and length and so on, and in style. Also, you have open notes, so make sure your notes are ordered and you don't start making stochastic measurements in your notes trying to find the solution because it's not in your notes. Okay, so for today we have quite a bit to do, so let's get right into it. We have to deal with all of the formalism of path integration or field integration, and on the way we'll also meet Grassmann numbers, and at the end we'll see a application of Hubbard-Satonovich, which I think you saw in class. So we're going to apply this to an interacting Bose-Einstein condensate as kind of the cherry on top of the cake for the end. Okay, so coherent states. Bosonic coherent states, just repeating in a minute what you've seen in class. So a fermionic coherent state is created out of the real vacuum, the empty space vacuum, by applying this exponent of a sum of creation operators. And of course, the way to actually read it is to expand this exponent into a Taylor series, and then you automatically see that a coherent state is a superposition of many Fock states. So it is not an eigenstate of a typical Hamiltonian, because it's a superposition of many Fock states. Right? Fock states are the eigenstates of the eigenized Hamiltonian. And the same thing can be done for fermionic particles in a very similar way, but now there's a minus sign, and in this case eta I are Grassmann numbers. In the former case, for the bosons, they're just complex numbers. And also here they're created out of the real vacuum. Phi is actually a function of time, or of this Euclidean time. And when I write phi of tau, it's actually a vector of many numbers. So there's a number where I goes from, say, 1 to n, where n eventually goes to infinity. So when I write phi just as a function of time, remember that there are capital N phis, and each of them is a function of this Euclidean time. And in the case of eta, the same thing goes, just that now they're Grassmann numbers, which are a function of time. So in the following, I will just denote in general psi, which is equal to either phi or eta, because a lot of the equations are the same for a bosonic and fermionic case. So I'll just write psi, and then if you have to figure out whether your particles are bosons and fermions, and then use either phi or eta according to what you have. So the typical integral that you have to solve is this partition function. Psi bar is the complex conjugate of psi. I'm writing bar instead of star, because that's the convention. And then e to the minus action, and the action again is a function of these coherent state numbers, complex numbers. And the action is given so it has two things. One of them is just the Legendre transform of, so it's the Lagrangian, right? But the Lagrangian is a Legendre transform of the Hamiltonian. So you have to express your Hamiltonian in terms of the coherent states. And then you add to this derivative, which is kind of like x dot p in analytical mechanics. And then there's one more term, which is mu times the number of particles. You can think of this, well, you can think of this just as the grand canonical ensemble, but you can also think of this mathematically. This is kind of a Lagrange multiplier, so it's a constraint on your system, and you use it because if you just want to minimize the action or minimize energy, the easiest way to do that is to take all the particles out of your system. But with this constraint, you can now use mu as a parameter, and mu is kind of like a volume knob, and it chooses the number of particles in your system, and this way you can force your ground state to actually have particles. So it's now more interesting, because now you actually have a system. Right? So that's the reason you use the grand canonical ensemble. Okay, let's, right, so what we usually want to do is, so this integral, right, it's e to the minus some integral, and then you have to integrate over all possible combinations of psi bar and psi. And in order to do this, it is easier to go, not to work in Euclidean time, but to work in the frequency domain, which is called, in this case, the Matsubara frequency domain. So you want to transform the various psi's, which are a function of time, into kind of a Fourier transform where you sum over all frequencies, e to the minus I omega n tau, and this omega n again depends whether you're using bosons or fermions. So in the case of bosons, h bar omega n, I'm not going to use h bar during the entire lesson, just for once to realize it's actually an energy. So for bosons, it is 2n pi times kBt, where kBt is 1 over beta. And for fermions, it is equal to 2n plus 1. And from now on, h bars equal to kb is equal to 1. So one piece of notation which is kind of confusing, you see this psi up here has two indices. One of them is n, one of them is I. I is this frequency over here is the same as I here, which is the same as the I here. So it's the mode, it's the eigenmodes of the Hamiltonian. N, on the other hand, is the sum for these frequencies, and it is instead of tau. So what I actually mean when I write psi n is kind of like the Fourier transform, which is a function of omega n. And it's the Fourier transform of psi of tau. So that's what I mean by psi n, and then the I is just that you have to transform each single mode, and that's why there's an I. So when I write just psi n without an I, what I mean is a set of numbers psi ni, where again I goes from some 1 to something infinite. In the same way that I'm using the psi of tau and the phi's. Okay, one more thing you have to know concerning Matsubara frequencies, and that's simply how to define a delta function. And then with this, you can do all of your computations. So as a first simple example, let's find the action of a non-interacting Bose gas. So the Hamiltonian, when we now have to express the Hamiltonian, so first of all, it's a Bose gas, so we're going to use psi equals phi, because they're bosons. And now we must express the Hamiltonian in terms, not of A dagger and A, but in terms of phi bar and phi. This is just done by replacing all of the A daggers by phi bar and all of the A's by phi. That means that the Hamiltonian, as a function of phi bar and phi, is equal to the sum over all modes, energy, and then phi bar k of tau times phi bar k, sorry, no bar, phi k of tau. And epsilon k is just the free particle energy, right? This is a non-interacting gas, so it's just k squared over 2m. Momentum over twice the mass. Okay, now we can plug this into the action. But one more thing, let me just mention, one more thing we'll need is the number of particles. So the number of particles expressed as a function of phi and phi bar is, well, what is the number operator? It's A dagger A, and then replace A dagger by phi bar, A by phi, so you get phi bar phi and sum over all modes. So it's the sum over k, phi bar k of tau times phi k of tau. Now we can plug this into the Hamiltonian, into the action, sorry. So we have sums, few sums over k, so let's take that to the beginning. So there's a sum over k. And there's an integral from 0 to beta d tau phi bar k tau d tau phi k of tau. That's the first part. Now I have the Hamiltonian, epsilon k phi bar k of tau phi k of tau. and the constraint minus mu there we go. Now we want to go to Matsubara frequency domain. So we're going to plug in every time we have a phi bar, we plug in the complex conjugate of this, so with a plus I. And every time we have a phi, we plug in this, and omega n, we put a note in our head that it's equal to 2n pi times temperature. We're using bosons. So what we have here is a sum over k. And now when we plug in this transformation, we're going to have a sum over n for each phi bar, another one for each phi. So we're going to have two sums. So there's a sum over n and over m. And I'm already going to shift stuff around. So there's a phi bar nk from here. And then here I have to take the derivative of this function. So there's a minus I omega m times phi mk. I'll keep the exponents for the end. And now I've moved everything that has tau to the very end, including the integral. This 1 over beta counts because I've used this thing twice. So I have in total beta to the minus 1, and then e to the minus I omega n minus omega m tau. So instead of writing the exponents every single time, I already shifted them to the end. But of course, I did this for an obvious reason. This is just a delta function. And that means that I can get rid of the sum over m. So we now have a sum over n and a sum over k. And notice that each of these terms now has a phi bar in the beginning and a phi with no bar on the right. So I can take the phi bars to the left, the phi to the right, and keep just these numbers, the omega, the epsilon, the mu, inside the brackets. So a nice way of writing this is phi bar nk minus I omega n plus epsilon k minus mu phi nk. So now you might also see why we prefer working Matsubara frequencies. This does look much simpler than this, right? And the reason we couldn't just take out the phi's here because we had a derivative, right? The derivative acts on this function. And here's no derivative, it's just multiplication. So it's much easier to look at. Once again, note that these two sums are two very different sums. The sum over n and the sum over k. K sums over all the modes, all the physical modes of the particles. The sum over n replaces the integral over tau. So it's not a physical quantity. It's the actual mode is, so for each sum over k, for each k there's a sum over all n's. So sometimes you have to sum over, it's more a mathematical thing, and the sum over k is more the physical sum. So they're two absolutely independent indices. What about the partition function? So that is now easy to write. And this is e to the minus sum over n and k, phi bar n k minus I omega n plus epsilon k minus mu phi n k. I'm not going to solve this integral, but you know how to if you did your homework. So I recommend that you try to solve this. Should be possible. It's a Gaussian integral of complex numbers. You should know how to do that by now. What I want to do instead is solve a different integral. For this, let me introduce the occupation number and how to evaluate expectation values in this field integral formalism. Consider an operator. Let's call it F. And you want to write this operator. I'll be general again for the moment, so I'm moving back to psi, and then we'll go back to phi and eta in a second. So I'll just use psi this time. So you want to write your operator as a function of the coherent state. And if you know that, then the expectation value of this operator is given by 1 over z times the integral psi bar tau psi of tau times this operator times e to the minus s action. So any expectation value you want to evaluate, you just have to plug it into here and then solve this integral and divide by z, which we've already found. So specifically, coming back to bosons, coming back to our example, let's look at the occupation number. For this non-interacting bosonic gas. Oh, and of course, similarly, let me go back one line. You could also do this in the frequency domain. So you could also do this as 1 over z integral over the frequency domain size. So after you've Fourier transformed, times f, which is a function of the size in frequency domain. So this is equivalent. So coming back to our non-interacting Bose gas, the total number of particles, the expectation value of the total number of particles is the expectation values summing over all nodes and expressed as a function of phi and phi bar. We already did this. It's the sum over k, expectation value of phi bar k of tau, phi k of tau. Now we have to translate to the frequency domain. So once again, plug in the Matsubara frequency, and what you get is phi bar n k phi n k. And here you see again what I've told you. For each k, there is a sum over n. After you compute this sum over n, and this is what we're going to do in a few minutes, you still don't have the total number of particles. You only have the number of particles in the kth node. So the sum of n is more like a mathematical thing to determine this physical index k, which is the actual node. And if you want to have the total number of particles, you have to then sum again over all the physical nodes. So let's see how we can compute this kind of expectation value. So let's look at the general formula, and we'll use the frequency domain. We've already computed S, right? It's this thing here. And we've now computed our F, which is NK. Actually, we'll just forget about the sum n for the moment. Let's just call this thing our operator without the expectation value. This will be our F. So the expectation value of phi bar MQ phi MQ, and I'm now switching, instead of n and k, I'm going to use m and q because I'm going to have a sum over n and k inside the action. I don't want to get confused. This is 1 over z integral d phi bar n phi n phi bar mq phi mq. That's this part here, right? It's the actual operator, and then I have to multiply this by the exponent of minus the action. So it's minus e, it's e to the minus sum over n and k phi bar n k minus I omega n plus epsilon k minus mu phi n k. So just to be clear, m is a specific value of n, right? N runs from, say, 1 to capital N, and somewhere in that series is this m. It could be m equals 5 or m equals 57 or whatever you want. And the same goes for q. It's one of the values that k obtains during the sum. Right? So we're looking for the expectation value of the qth frequency of the mth node. And also this should look kind of familiar. Specifically in your homework, you solved or you proved this following identity. There you showed that the expectation value of, so for a infinitely long vector, or a vector that is capital N long, and you're looking for the expectation value of two of the entries of this vector, the mth and the nth entry, then it is equal to, forget about this for the moment, this integral with the Gaussian, right? V dagger V, it's a Gaussian, and A is the matrix that is between these two vectors. And this is where that doesn't make sense. And this is the actual thing that you're trying to compute the expectation value of, and then it's weighted by this partition function, by this distribution function. You sum over all the entrances of the vectors, and then this thing is normalization. This is actually just 1 over z, which was, I think, section A, and this was section C of the same question, right? And so what we actually have to solve up here is exactly the same thing. We're trying to solve this integral where this thing is 1 over z. So in analogy to what we're trying to do, this thing is 1 over z. This thing here is the integral phi bar n phi n. This thing here is the actual thing we're trying to compute. It's the phi bar mq psi mq, right? The bar is instead of the star. And then this thing here is the exponent that appears there as well, right? The sum over nk, blah, blah, blah. So what must it be equal to? It must be equal to the element mq, comma mq, because, well, here we had only one index, m and n, but here m stands for two indices, of the inverse of this operator. This is our A. Now, because n and k are independent indices, this operator is a diagonal operator. You also see that because the phi bar on this end and the phi on the other end have the same index. It's not n and m and k and q. It's the same indices. So it is a diagonal operator. And that means that the inverse of a diagonal operator is just a diagonal operator with 1 divided by the entries of the diagonal. So what this is equal to, making a long story short, it is this operator, 1 divided by this operator, I omega n plus epsilon k minus mu, where n and k run from 1 to infinity, but you have to take out the value, or the expectation value between mq and mq. So it's at mq, or at n equals m and k equals q. And bottom line is that this expectation value, I'm switching back to n and k, is equal to minus I omega n plus epsilon k minus mu, 1 divided by this, and then nk, which is equal to 1 over beta sum over n of this expectation value, is therefore the sum over n t divided by minus I omega n plus epsilon k minus mu. For those of you who have a headache, I've only just started. What we want to do now, I mean, this was nice math, but we haven't really learned anything yet. I don't know what this means. Right, the number of particles in the kth mode, or the average number of particles in the kth mode is this. What does that mean? So what we have to do is solve this sum over n. So we have to sum over all Matsubara frequencies, and that's why this is called Matsubara summation, because summing over all Matsubara frequencies. So let's do some general stuff first and then apply it to our case. So we're going to consider some function of the Matsubara frequency, which looks quite similar to our function. It's minus t over I omega n minus c. So the actual sum that we want to solve is the case where c is equal to epsilon k minus mu. And we want to solve the sum over this h of omega n. And I will do the bosonic case, and then you can do fermions at home. So first of all, we introduce some function, g of z, where z is a complex number, and this will be equal to beta over e to the beta z minus 1. That is just a complex number, or complex variable. And we're now going to evaluate the closed contour integral over g of z times h of minus iz. So we're going to use the same h, but instead of using omega n, we're going to plug in minus iz. And I have to tell you what the contour is. And for this, let's make a little drawing. So this is the imaginary plane. This is the real axis of z. This is the imaginary axis of z. And the contour I'm going to take is, I'm going to move all the way up like this, and all the way down like this. And at plus and minus infinity, they join. So this is at minus infinity, minus I infinity. And the same thing happens at plus I infinity. So it's a closed contour integral. I go all the way up to infinity, up to the left, all the way down to minus infinity, and around again. Now, why the hell would I do this? So g of z was not just by chance chosen as it is. Notice that the poles of g of z are when z is equal to the Matsubara frequency. So when z is equal to I omega n, remember that omega n is 2 pi n divided by beta. So if you plug in z is equal to I omega n, the beta cancels. You get e to the 2 pi n, which is equal to 1. Then 1 minus 1 is 0. So these are the poles of g of z. So these poles lie here on the imaginary axis. These are all the I omega n. For n equals 0, n equals 1, n equals 2, n equals minus 1, n equals minus 2, and so on. And that's why I can only close the contour at infinity, because all of these poles are distributed along the complex axis. So this integral is equal to right. Okay. So how do you evaluate a complex plane integral? There's this really cool thing called the residue theorem. So we can use the residue theorem. We already found our poles. So this integral must be equal to the sum over all residues, or 2 pi I, times the sum over all residues of g of z times h of minus iz. And where are the residues? So all the residues is basically the same as summing over all Matsubara frequencies. Because at each Matsubara frequency, there is a pole, and each pole is a residue. So I have to sum over all Matsubara frequencies, and to find the residue, you have to plug in the residue, right? You have to sum over all of them. Okay, so let's find the residue of the nth Matsubara frequency. So how do you find the residue? You take the function and multiply by z minus the pole. Remember? If you don't, then, well, that's not a good sign. You're supposed to remember what you learned a year ago, or 2 years ago. For the residue g of z times h of minus iz at z equals I omega n is equal to z minus where the pole is. That's the thing that will make the function well behaved, right? You cancel out the term in the function that blows up. That's why you multiply by this bracket. And if we do that for our function, we get beta times z minus omega n divided by e to the beta z minus 1 h of minus I z at z equals I omega n. I haven't actually plugged in the pole yet. And the reason I haven't plugged it in yet, so whatever this is going to be equal to when I plug it in, that's the residue. But why can't I plug it in? Well, because if I plug it in, I get I omega n minus I omega n, that's 0. And here I get e to the 2 pi n minus 1. Well, that's 0. So I'm dividing 0 by 0, and I'm lost. So I go back another 2 years in education, and I remember, not Taylor, L'Hopital, right? So I have to take the derivative of the top, derivative of the bottom. Yeah, so much of my physics degree in one lesson. It's amazing. So let's take the limit where z goes to I omega n, right? Of beta z, that equals, I'm going to use this, of z minus I omega n divided by e to the beta z minus 1. So let's take the derivative. So there's beta, and then the derivative of the top is just 1. The derivative of the bottom is beta times e to beta z. Beta cancels. Plug in z goes to I omega n, you get 1. Bottom line, the residue, so all of this is equal to 1, right, what we just found. All of this is equal to 1 when you plug in this, and so all you have to do now is plug in z to h, so you find that this is equal to h of omega n. So what I'm telling you is that this integral, this contour integral over this made-up function and I omega z, that is equal to the sum over all n, so 2 pi I times the sum over all n, and then the residue itself is equal to h of omega n. With me? Okay, so I've done some intermediate step to calculate the residue. And now you see that if I want to calculate this sum, remember that this is what we want to calculate, the sum over all h omega n. That's what we want to calculate. That was our goal in the beginning. And I've now proved to you that instead of computing this sum, you can just compute a complex plane contour integral. And what you should be saying is, okay, this is easy and this is hard. I don't know how much complex analysis you remember, but this should be easy, or easier than computing a sum. If it's not, then that's a math problem, not a physics problem. Because any mathematician will tell you that this is much easier. And you know it's much easier. I'll actually show you in a second how easy it is, for those who don't remember. In any case, bottom line, or not bottom line, intermediate line, sum over n h of omega n is equal to, I'm just going to move the 2 pi I to the other side, so it's equal to 1 over 2 pi I. Closed contour integral, this is my contour, I've already defined it, over this g of z times h of minus iz dz. That's it. So now we have to actually evaluate the integral. So in order to evaluate the integral, we have to do two things. What do we have to do? So let's plug in our value, our h of omega. So we have to integrate, let's write down again, g of z, h of minus iz dz. This is equal to the integral, or minus the integral over e to beta z minus 1, z minus c, dz. So all I've done is plugged in g of z, which I've introduced, and I plugged in h of omega n, which is this thing here. So the beta times t is equal to 1, because beta is 1 over t, and there's a minus sign on the outside, and instead of writing omega n, I've written minus iz, so I omega n is then equal to plus z. So how do I evaluate this integral? Well, let's look at our complex plane once more. So we already spoke about the poles arising from g of z. There is one more pole. Let's see, right? Z equals c, and c is, let's assume it's real for the moment, so c will be somewhere over here. But the contour that we are summing over is this thing that goes all the way up here, joins at infinity, all the way down, and joins again at infinity down here. But remember that in complex analysis, you're allowed to move around, you're allowed to deform your contour as long as you don't cross any singularities. That ring a bell? I hope so. So what you can do is make this kind of circular. The only thing you have to work, so you can extend this point and this point out to minus infinity and plus infinity. The only problem is you can't cross that equals c. So what you can do is just be careful not to cross this point. And now I'm going around the same way still, so I'm going around like this. And the solution of the integral using the black contour or the red contour must be the same, it must be to the same value, right? So let's use this new contour. And now I'm going to use a trick. So when you go around this contour, so the radius of this contour is r, and r goes to infinity, and the contribution from that part cancels. And then there's the integral of this part going in and this part going out, and they are equal to each other because they're basically on the same line. So they cancel each other, and you're actually only left with the integral going around z equals c. This is the only contribution that survives. But this is now going counterclockwise, so you add a minus sign. So this must be equal to minus 2 pi I times the integral around this black contour, the little black contour, which is just the residue at z equals c. So it's minus 2 pi I times the residue at of g of z h minus iz at z equals c. Yes?
How can you say that all of the circle cancel out? Because
so you can actually do it.
A small portion at im equals 0 on the left side, and that should cancel out the.
At im equals 0?
Yeah, like when you go to the all the way to the left.
Yeah.
Yeah, where is this part canceling?
No, it cancels because r goes to infinity. So if you take e to the beta z, and then z is equal to r, and r goes to infinity, then this thing becomes infinite, and 1 divided by infinity is 0. And it happens all around. There's some fancy name for this theorem in complex analysis. I forget the fancy name. It's named after some guy, some crazy mathematician. But this almost always happens. Not always. It's interesting when it doesn't. But it almost always happens. I'm not going to get into this. It's part of complex analysis second year. The point is that the large arc cancels, the one coming in, the one coming out cancel each other. You're left with only the circumnavigation of the pole itself, and that is just the same as going counterclockwise around this. So instead of evaluating this big red contour, I can evaluate this little black contour, and that is equal to the residue of the pole. But since I'm going around in the opposite direction, right, counterclockwise instead of clockwise, clockwise instead of counterclockwise, you get a minus sign. But it's the same residue theorem. Okay, cool. So all we have to do now is evaluate the residue. So this is equal to, so let's plug in g of z and h of iz. So I have two minus signs, that gives a plus sign. So there's 2 pi I. Let's make the residue, so I have to do z minus c for the residue, right? You have to take off, do z minus the pole, and then e to the beta z minus 1 z minus c, and this has to be evaluated at z equals c. So you cancel this. No problem with nothing here is divided by 0, so you can just plug in z equals c, and you get 2 pi I times 1 over e to the beta c minus 1. Okay, that was easy. Now let's put this back into the general formula here. So the sum over h of n I'm summing over all n is equal to 1 over 2 pi I times this integral. This integral is equal to 2 pi I times the fraction, so 2 pi I cancels, and all I'm left with is 1 over e to the beta c minus 1. Cool, right? I could have expected that just by looking at the function in the beginning, right? Okay, obviously not. That's why we went through all of this in detail. Let's go back to our example of occupation number. So for occupation number, we wanted to evaluate this sum, which is the same as this h of omega n, but with c equal to epsilon k minus mu, and that means that the solution, n of k, which is the sum over all of these functions, is 1 over e to the beta epsilon k minus mu minus 1. Look familiar? Not Bose-Einstein, Bose-Einstein? Is the other guy? Yeah, Bose-Einstein.
Minus 1, and the other guy is the plus 1.
The other guy, yeah. It's the partition function that you're used to, the mean occupation number that you know.
Something we learned in the
Something you learned,
physics
yeah.
in the last year.
You got it. Okay, so now we proved it. We haven't proved it, you knew it already. But you see, it makes sense. Okay, nice. Second topic for today, Grassmann Gaussian integrals. Let's go over this quickly because we still have to get to the main topic, or to the most exciting topic. So let me just remind you, Grassmann numbers are these weird numbers in quotation marks that when you flip the order, well, you get a minus sign. The funny thing is that when Grassmann was not a physicist, he was a mathematician, and he lived long before anybody could even dream about such a thing as fermions. And when he started thinking about Grassmann numbers, he just thought it would be cool to think about numbers with anti-commute. Not quite sure what he was on, but when physicists came along, like, I don't know, 100 years later, and discovered fermions and anti-commuting operators, then they had this, I don't know if it was a book, but a lot of a whole mathematical basis just sitting there waiting for them, ready for using. So suddenly Grassmann became very famous in physics, although no one ever dreamed that this theory would have any application. So thank you to Grassmann for being crazy. Okay. This, of course, means that take any Grassmann number squared, you get 0. That's obvious. This means that if you want to Taylor expand some function of a Grassmann number, well, that's actually very simple. And that's it. And this is not an approximation, this is the entire sum. This is the infinite sum. All other terms are identically equal to 0 because of this property. What about having two variables? So this is for a single variable. A function of just one Grassmann variable. For two variables, which you could just take as eta and eta bar, because a complex number is two variables, right? It's x plus iy, so it's x and y, and you can think of the two variables sort of being x and y. You can think of them being x plus iy and x minus iy. It's just a different way to express them. And in this case, you get, if you Taylor expand this function, you get 4 terms. Sorry, you get 5 terms, because now you also have to take into account the second derivative. Zero, zero, eta bar, eta, and then the other way around. And of course, these last 2 terms, if these were just normal numbers, then it would be the same term, and you would forget about the 1/2, which is right, the 2 of them. But because these are Grassmann numbers, it depends whether you take the derivative with respect to eta bar first or with respect to eta first. So this is the definition. This is the definition, and this is just a direct consequence. Well, plug in I equals j. Which number equals the minus of itself? Right, only 0. Right. It's like with Fermionic operators. Right, there's nothing new. If I would write a dagger I, a dagger j, right, it's the same thing. Okay, so let's apply this to a Gaussian. So e to the minus eta bar a eta, you can use either the single variable formula and just think of eta bar times eta as a single variable, or you can use this more complicated formula. In both cases, I invite you to go through it. You get 1 minus eta bar a eta. Okay, let's do the Gaussian integral for the single variable case. So I'm integrating over eta bar and over eta e to the minus eta bar a eta. And the easiest way to do this integral is just to expand into Taylor series and then solve each integral individually. So there's only 2 terms in the expansion. So there's 1 minus eta bar a eta. Now the integral over 1 is equal to 0. You prove that in the lecture. Write it down on the side. So the integral d eta is equal to 0. And the integral over d eta times eta is equal to 1. You prove this in the lecture. At least I hope you did. You were supposed to. So this 1 just gives 0, and then you're left with the minus. So there's an integral d eta bar d eta minus eta bar. And let's put this eta here and a in the beginning. A is just a number. You can put that wherever you want. Now to do this integral, you cannot do it yet. First you have to switch the order. So you get eta times eta bar and no minus sign, because you switch the order. So this is equal to a times the integral d eta bar, integral d eta times eta bar. This is equal to 1. And then it's irrelevant, and the integral of d eta bar d eta is also equal to 1. and you're left with A. This is very different from what you're used to from complex numbers. In complex numbers, this would be equal to 1 divided by A, or pi divided by A. Now it is equal to A with no fraction. Right? It used to be in the denominator, it's now in the numerator. So this is maybe a little surprising. If you go through the math as you did in the homework, you can show that for the multidimensional case, so here eta was just a single variable. Now when I write eta, I mean a vector of Grassmann numbers, which could be as long as you want, infinitely long if you want. So it's e to the minus eta dagger some operator A times eta. This is equal to the determinant of A. Not 1 divided by the determinant of A, but the determinant of A. And likewise, you can show that the integral over a Gaussian with a source term, so e to the minus eta dagger A eta, but now I'm adding a source term nu, so plus nu dagger eta plus eta dagger nu. This is going to be equal to the determinant of A times the Gaussian in nu, with A to the minus 1. That's the same as in complex numbers in a second. That's the same as in complex numbers. It's the inverse. The width of the Gaussian is the inverse, and you get a Gaussian in the new variable, in the source variable. And one more thing that you can show also, you advance in exactly the same way as you did in your homework, namely that's that the expectation value of two Grassmann numbers, or some functional Grassmann numbers, which is defined as 1 over the determinant of A integral eta bar eta. And then you put in this function eta j, eta I bar, and then you have a Gaussian e to the minus eta dagger A eta. This is just equal to the inverse of the matrix A, element ji. So exactly the same as in all other cases. Okay, so this, I'm not proving this to you, although I have proven this in my notes, and these I'm just giving you, but you can go over this and you can do this exactly in the same manner as you did for the real multidimensional Gaussian and the complex multidimensional Gaussian. The exact same thing, just taking, remember that you're using Grassmann numbers, and you will arrive at these formula. Questions? So a Grassmann variable, you think of them as, they're the same as regular numbers, so it could be a complex number, right? But the difference is that when you change the order of two Grassmann variables, then you get a minus sign. But otherwise, you can have, when I write eta like this, right, as a vector, say, you could have, say, eta x, eta y, and eta z, right? And then the dagger is, right. Yeah, of course, these are complex numbers, right? There's also an eta bar. That's the complex conjugate of eta.
So it can also be complex, but the only difference between this and complex numbers is that
when you reverse the order, you get a minus sign. That's the only difference where all of the complications come in, right? But yes, that's the only difference. That is correct. Other questions? Any other question?
no, it will be.
Okay. BEC, Bose-Einstein condensate. So we're going to consider a Bose gas, a gas of bosons. with contact interactions. And what contact interaction means is that these bosons behave like billiard balls. They only interact when they bump into each other. Simple as that. That means that the interaction potential of two particles, one particle at r and one at r prime, is equal to a delta function. There's only interaction when r is equal to r prime. If two bosons try to occupy the same position in space, well, they bump into each other. But if they go past each other at the distance of half a nanometer, they just pass next to each other and don't bump into each other. Okay, that's what's called a contact interaction. It's the easiest type of interaction, and it's actually the dominant interaction inside the Bose-Einstein condensate. So this is a very good approximation for what's going on. Okay, so what is the action? So we're going to write down the action of this gas in terms of bosonic coherent states. So look back to the beginning of the tutorial. I'm just going to plug in the Hamiltonian, which is H naught plus interaction, and H0 is just the kinetic energy. So there's a term phi bar of r and tau, and there's a d tau. That was the first term in the action, plus H0, which is the non-interacting part, minus mu, which was our Lagrange multiplier, phi r of t. And then there's the interaction term, which I'm taking outside. And I had to take this outside because in the interaction term, phi appears 4 times. Right? Remember that there's a dagger, AA, right? But then you plug in this delta function, you get rid of some indices. So there's a phi bar of r and t times phi of r and t, and all of this squared. And now I can close my bracket. Tau, yeah, sorry. Yeah, this is tau. We're using Euclidean time. Not that it really matters. And you can rename tau as t and just not think about Euclidean time. But yeah, let's go to Euclidean time. And this H0 is the operator minus Laplacian over 2m. I'm writing it in position space because my field is currently, or the bosonic operators are currently in position space. I'm going to fix that in a second. So this is the general Hamiltonian. Let's keep that for later. And let's start with the non-interacting BEC. So G equals 0. What happens in a non-interacting BEC? So we've already talked about a non-interacting Bose gas in the very beginning of the lecture, and we already transferred it into Matsubara frequency domain. So I'll just remind you what we got back there. Minus I omega n plus epsilon k minus mu phi n of k. Remember? It was a long time ago. But it was after complex analysis, so you have no excuse. Okay, now let's use our physical knowledge. BEC means that the ground state, k equals 0 and n equals 0, will be macroscopically occupied. So let's take that term outside of the sum. And the term with k equals 0 has 0 energy because k squared over 2m for k equals 0 is 0, and omega n for n equals 0, it's 2 pi n times kBt for n equals 0 is also 0, so you're only left with mu for the 0th term, so you have minus phi naught mu phi naught, and then you're left with the sum over n and k different from 0 over this stuff, phi bar n k minus I omega n plus epsilon k minus mu. And if you want, you can now write the partition function z. I'll call it z naught because this is s naught for the non-interacting postgas. If you take the logarithm of that, add a minus sign and multiply by temperature, you get free energy. And if you then take the minus the derivative of the free energy with respect to chemical potential, you get the number of particles. I hope this is not new to anyone. So then you get phi bar phi plus the sum over nk. If you take the derivative, so e to the minus this thing, and then the derivative with respect to mu, then you just take down a phi bar phi. So you're doing the integral over phi bar phi times e to the minus the action, which we spent about half an hour on showing that this is just a sum over all nk. What is the absolute ground state? Well, in the absolute ground state, all particles go into the ground state. So the number of particles in all states for k different from 0 is equal to 0. And the average number, this thing, you can call this thing n0, the number of particles in the condensate. And in the ground state, n0 is equal to n, so all particles are in the condensate. So we can write a simplified version of the action for the ground state, which includes only the k equals 0 term. So for the ground state, n0 is equal to n, and nk is equal to 0 for all k different from 0. In this case, you can write S naught as minus mu phi naught bar phi naught. As easy as that. Okay, that was simple. What about the interaction? So now let's talk about a weakly interacting BC. And we're going to do mean field. Later on, we're going to do beyond mean field. So to do mean field, we have to introduce the interaction. So the action will be equal to the non-interacting part plus the interacting part. And the interacting part is this thing here with the integral over tau and over d3r. But we're now going to use k-space and use only the k equals 0 contribution, because we're assuming that we're in the ground state. And we're going to use the Matsubara frequency instead of tau. So you do all of the transformations, and what you're left with is just g over 2 phi bar naught phi naught squared. It's quite obvious, but I encourage you to do it. So the total action is equal to minus mu phi bar phi plus the interaction term, and therefore the partition function is equal to the integral over phi naught bar phi naught e to the minus action, so you get plus mu phi bar naught phi naught minus g over 2 phi naught bar phi naught squared. So try for a second to look at this integral let's go back quickly to the case where G is equal to 0, so there's no interaction. What does this tell you about mu? Let me ask the question differently. What happens if G is equal to 0 and mu is positive? What is the solution of the integral? It's not a Gaussian. There's no minus. It's infinite. Right? If there would be e to the minus mu phi bar phi, then it's a Gaussian, and it's just whatever was in the homework, right? But this is plus mu, so if mu is positive and G is equal to 0, and this explodes, so this tells you that the chemical potential must be negative if there's no interaction. What this also tells you that if G is negative, and negative G means that interactions are attractive, so if G is negative, then you get a plus sign here, and it also explodes. So this tells you that in order for the BEC to be stable, in the presence of interactions, these interactions have to be repulsive, right? So you need G larger than 0, which means repulsive interactions, and then mu could be positive. But if G is equal to 0, mu has to be negative. Let's make a plot of the action to try to understand some of the physics here. And I'm going to plot the action as a function of the real and the imaginary part of this ground state field, phi naught. It's an imaginary number, so I can plot it in the imaginary plane. And on the z-axis, I'm going to plot the amplitude of the action. And I'm going to use this case where both G and mu are positive. So it is equal to minus mu, something that looks like phi squared, plus G, something that looks like phi to the fourth. Right? So what this looks like, it's difficult to draw this stuff, is something like this, something like a W, right? But it's three-dimensional, so does this make sense? And it goes around here as well and through the back. This is sometimes called the Mexican hat, because it looks kind of like a Mexican hat, right? Bulb in the middle and it goes up on the sides. Right? That's what I'm trying to draw. There's a more convincing drawing, yeah, like a sombrero. And there's a more convincing mathematical drawing, like a computer drawing in the notes. But what this tells you, so let's use our physical intuition. The ground state, or the classical state, which is the equilibrium state, is a state where phi is, oh, my axes are totally out, is where the action is minimal. Let me just try and show that this point here, exactly below the tip, in the center of the circle, that is the point 0, 0, where both phi and phi bar are equal to 0. So you see that to get minimal action, you need phi, the absolute value of phi, to be different from 0. In fact, you want phi to be equal, whatever its value is, on this circle. Right? That's the minimum. There's a degeneracy. It could be equal to any one of those, so the phase can be arbitrary, but the amplitude of phi, the absolute value of phi, needs to be equal to whatever it is on the circle. And to find that, you can just use Euler-Lagrange, because that's what Euler-Lagrange gives you. It gives you the least action. So applying Euler-Lagrange, dl d phi naught, notice that there are no derivatives of phi in the action. It's just phi naught, so you can forget about the second part. You only use the first part of Euler-Lagrange. So from dl to d phi naught equals 0, you get mu phi naught bar minus g phi naught bar squared phi naught. This has to be equal to 0. We already said that we don't like the solution where phi naught is equal to 0. It's a maximum, a local maximum, so it's unstable. It's an equilibrium point, but it's an unstable equilibrium. And it's a trivial solution because it means that there are no particles in the system. So you can now divide by this phi naught bar, and you find that the absolute value of phi naught is equal to the square root of mu over j. Mu over g, sorry. So the ground state wants to have particles inside it. How many particles? Phi bar times phi, which is just this thing without the square root, mu over j, mu over g. That's the number of particles that will minimize the action in the ground state. Okay. Okay, great. Now we can do beyond mean theory, beyond mean field. That's where it gets interesting. Okay, so what have we learned? I'm now going to switch back to R and tau instead of K and omega, or K and N. And the reason is that in beyond mean field, we'll have to get to consider some stuff that happens outside the BEC. We have to consider excitations. Right, so mean field gives us the equilibrium, the ground state. The question is, what are the excitations in the BEC? What are the elementary excitations when you put in just a little bit of energy? So I'm going to use this field phi of r in tau, and I'm going to expand it, or I'm going to write it as a complex number. It's the square root of something I call rho times e to the I theta. Both rho and theta are real fields. Phi bar phi tau, sorry. And the value of, and the point is to do beyond mean field, I have to take this rho and I'm going to expand it around the stable minimum rho 0 plus some delta rho, which is a function of r and tau. And this rho is the value at equilibrium. And since rho is equal to phi squared, right? So this is equal to phi naught squared, which is equal to mu over g. So coming back to this drawing, let's take this drawing, but look at it from the top. Make it a little easier for me. This is the real part of, sorry, what am I doing? Real part of phi naught, imaginary part of phi naught, and then this circle here, that's the circle here, right? It's the ground state. The radius of this circle, well, it's in phi, so it's the square root of rho. And I'm now looking at small fluctuations around this equilibrium. And these equilibrium and these fluctuations are described by the field delta rho. And I'm going to assume, obviously, that delta rho is much smaller than 1, such that this assumption is valid. I don't have to keep any higher order terms. And in our substitution, theta is the thing that goes around the circle, but theta I can't approximate because you can choose, right, that there's no barrier, it doesn't go up in the action, it doesn't cost anything to go around theta. So that can just, it doesn't have any influence, or I cannot do a small order expansion in theta. It could change by pi, I wouldn't even notice it. But if delta rho changes, that costs energy. So let's look at our action, and this is our action. It's good thing it's still up here. So let's continue from here, and let's plug in this substitution. Right, we have phi here and here, a couple times here. So everywhere where I see phi, I'm now going to plug in the substitution. Okay, you following? It's really hot in here. You following? Is it just me? Okay. Maybe it's too easy. So let's do the interaction term first. When I plug in the substitution, so let's call it star, so I'm plugging in star. What I get up here, that's the easy part, is G over 2 rho squared. Right, because it's a phi bar phi, that will cancel the I theta, the e to the I theta. And you're only left with rho, but you have square root of rho to the power 4. It's rho squared. That was easy, right? Don't look so puzzled. Now let's do the this part. Well, we'll get back to the integrals in a second. So phi bar d tau plus h minus mu times phi. This is equal to square root of rho e to the I theta. All of the phi's and rhos and thetas are all functions of r and tau, but it's going to be quite long without me writing the arguments every single time, so let's just remember that these are the arguments. So there's a d tau, and I have to take the derivative of rho e to the I theta, where both rho and theta are functions of tau. Okay, so there's two derivatives, and you get d tau square root rho plus I rho d tau theta minus 1 over 2m. Laplacian of rho plus I2 square root rho d theta minus square root rho Laplacian, sorry, d theta squared. Close the brackets, minus mu times square root rho times e to the I theta. I haven't done anything complicated yet. The only thing I've done is derivatives. So derivative of tau, then the Laplacian acted again on the rho and theta. I have to do it twice, and it's a product, so you get a bunch of terms. But this was still trivial, and I'm missing a minus sign somewhere. This would be a minus I theta here from the phi bar, which is a complex conjugate. And then obviously you can cancel e to the I theta with I theta, right? You can now just move it through. Of course, we've done all the derivatives already. Before we did the derivatives, we couldn't do this. After we've done the derivatives, we can just move I theta, e to the I theta to the beginning, and they cancel. And now comes the magic. So what a physicist does is he looks at these terms, and he thinks, which of these terms can I use mathematically, and all the others I'll somehow get rid of. Right? And then in the end, I'll come back and justify why I get rid of them. So let's see how much time we have. Okay, so let me write down what happens after you throw away the bad stuff, and then I'll do the actual thing that I want to get to, which is the actual Harbitz-Stratonovich. You have the details of how to get from this to the next expression in the notes, and I'll write it down and then also say a word about the test where something like this might happen. So let me write down the expression so you can find that this is approximately equal to. Remember that I haven't plugged in this approximation yet. Okay, so I'm now going to plug in this approximation, and I'm going to neglect higher orders of delta rho. I'm going to keep only the leading order, and it turns out that all the linear terms cancel, as always, and you're only left with the quadratic terms. Actually, this is obvious we're expanding around a minimum, so you expect the linear terms to cancel. That's the definition of a minimum. And that's why the quadratic terms is the next leading term. So that's not surprising, that kind of could be expected. So what you're left with when you do all of this is I delta rho d tau theta plus rho 0 over 2m div theta squared plus g over 2 delta rho squared. That's it. So when you prepare for the test, you're going to start opening the previous lessons, the previous exams, and you'll see that quite often you will have something like this, and then you will be asked to find something like to simplify it with an approximation. And typically, if that will ask in the question, show that this is equal to this. So you know what you're trying to get. So if you don't manage to throw away the stuff you need to throw away, you can always continue to the next section and use this solution, so don't be stubborn. And since you know where you're going, all you have to do is find a good enough argument to neglect all the stuff you don't like, right? So when it comes to real-world physics and in your research you encounter this, well, then you're really puzzled. You have to start using your intellect, and getting from here to here might take you a year, and sometimes does. But on the test, you know where you're going. Someone's done it before you. Just make it look convincing that you get there, right? Of course, the complicated part is actually doing it for the first time. But again, that's not what we're trying to study here. We're trying to understand some machinery. So now we have this easier form. Actually, I shouldn't have this part here. This is, sorry. This is interaction, but I'm only using the non-interacting part. But now we can write down the partition function, or we can write down the action, the total action. Let's just make sure we have that. The action is now a function of delta rho and theta, right? Because rho itself is equal to rho 0, which is a constant, plus delta rho. So the actual field is now delta rho. And theta remains as it is, and this is equal to the integral d tau, integral d3r, non-interacting part, which is I delta rho d tau theta plus rho 0 over 2m div theta squared plus g over 2 delta rho squared. So it's a Lagrangian with some weird stuff for theta. I have no idea how to interpret that. But in rho, it's very simple. It's quadratic. And you already know that quadratic stuff can be diagonalized because we love harmonic oscillators and we love Gaussians. And we love nothing else. So partition function is the integral over all of the arrangements of delta rho and so it's the integral d delta rho and the integral over all configurations of theta. So it's all configurations of the field, of the two fields. Yeah, sorry, theta. E to the action, so e to the minus s delta rho theta. And I'm now going to, right, because delta rho appears here and here, but not here. So let's take these two integrals apart. Let's first write the integral over all configurations of the angular field of theta, e to the minus integral d tau, integral d3r, rho 0 over 2m, div theta squared. And this is now multiplied by the integral over all configurations of the field delta rho, e to the minus d tau d3r, and whatever contains rho. So this has the interaction term g over 2 delta rho squared plus I delta rho d tau theta. Great. And it turns out we can actually compute the integral over delta rho. And that's what I wanted to get. So all of this was like introduction. Now we're actually doing the integral. And let me try and teach you something about how to solve these kind of integrals. It looks a little weird and a little disturbing when you look at it for the first time. But you notice that this is actually quite easy if you stare at it for a little bit. So first of all, notice what are the two variables? So the two variables that we have are delta rho, which appears here and here. That's the thing we're integrating over, right? And then the second variable is d tau theta. Don't be worried about d tau theta. You can just call, make up some new variable. Alpha is equal to d tau theta. Who cares, right? So what is this? This is a Gaussian in the first variable times I plus I that variable times some other variable. What is that? Fourier transform. Right? If I would write x squared plus ixk, it would be simple. But that's exactly what I'm writing, just using different names. So that's the first thing to note. This is kind of looks like it's kind of like Fourier transform. So what you expect, right? What's the Fourier transform of Gaussian? Well, it's a Gaussian in the new variable, right? So you expect something that looks like e to the minus d tau theta squared, and you expect it to be, so the width of the Gaussian has to be 1 divided by this width. So it must be divided by g, because here it's multiplied by g. I haven't really calculated yet, but it's just what I expect by looking at this. This is gx squared plus ikx, so I expect k squared divided by whatever is here. The next thing to note is that integrals are actually just sums, or approximately equal to sums. They're equivalent to sums, and therefore this is just a multidimensional Gaussian integral. Homework, we've done that before. So you should notice that this is just a real multidimensional Gaussian integral. And why am I stressing that it's real? Because you know that delta rho and theta, they are real fields. That's how we defined them a few minutes ago. So you have to use this formula that you looked at in the homework. It's e to the minus v transpose matrix A v over 2. And then you had the source term jt dot v. And you showed that this is equal to the square root of 2 pi to the power n over the determinant of A times the Gaussian e to the j a minus 1 times j, there's a transpose here, over 2. So let's figure out how to translate this from integrals to sums. I'll do this carefully, even though we're over time, just to make sure that this point is clear. But this is one of the main mathematical tools when you use field integration. And it's really good to know it. So this first term in the integral, v transpose a v, well, this is actually just the sum over I and j, vi, ai, j, vj. And in our case, this is the part which is integral d tau and d3r. Right, we're summing over all arguments of our functions times delta rho times g times delta rho. Right, that's this part here. And the 1/2 is taken care of in the formula already. Right, the 1/2 is here. And the second part, the j transpose dot v, well, that's just a sum over I, j I v I. And this, in our case, is the integral d tau integral d3r. I delta rho times d tau. Should be a theta, right? Theta. It's a mistake on my notes, sorry. Correct it when I finish off here. So now we can, so what does this mean? We're just identifying that A is our J, is our G, right? A is G, and V is delta rho, and J is I d tau theta. So we just plug all of this into the solution, and what we then find is that the integral over delta rho, this part here, so let's not care about this square root 2 pi n. I don't care about that part. I'll explain in a minute why I don't care about it. But this I is then just proportional to e to the minus integral d tau integral d3r d tau theta squared divided by 2g. Guess what? A Gaussian in dt tau, in d tau theta. That was to be expected. And that means now that the action, remind you, the action is whatever is written up here. And it used to be a function of delta rho and theta, but we've integrated out delta rho, so it's now a function of only theta. And what we're left with is whatever's written up here, and well, this part as well, because we didn't do anything with that. So we have 1 over 2g d tau theta squared plus rho 0 over 2m with theta squared. So this, let me stress what has happened. This might not look very cool, but it's actually very impressive, because we started off with an action that involved two fields, delta rho and theta, and by using the formalism of field integration, we could get rid of one of them. We basically integrated out over this delta rho, over these fluctuations around the minimum, and we're left with a action that contains only theta. And now we can say something about the dispersion relation and about the behavior of the excitations in theta. If you look at this action, well, you should recognize what kind of action this is. You've seen this action before. Not very long ago. Beginning of the semester. It's missing something for Klein-Gordon. It's missing a mass for Klein-Gordon, but it's Klein-Gordon without a mass. In other words, it's the 1D chain. Right? There's a derivative with respect to time squared, and a derivative with respect to space squared. This is a 1D chain. This describes something like phonons, a massless relativistic particle. And if you look back there and see and look at the dispersion relation is just the coefficient of this divided by the coefficient of the other derivative. So you see, first of all, theta describes a massless excitation. And the dispersion relation omega k where did my k go? Okay, to get k, I have to actually go to k space, and then from here I'll get a k squared. And you can find then, do exactly the same thing that you did for the 1D chain, and you find that the dispersion relation is g rho 0 over m times k. This is the dispersion relation of the excitations. They are phonon-like. These modes are called Goldstone modes. They are massless excitations. And let me just tell you that if you go beyond mean field and do the same thing for delta rho, you can kind of tell already, because delta rho is squared, and that means that it is a massive field. And so the excitations in delta rho on the amplitude, not on the angle, but if you go up inside the Mexican hat, then you get a massive dispersion relation. So something that goes like square root of k squared plus some mass squared, and that is called the Higgs mode, and it has everything to do with the Higgs boson, which you might have heard of, and this is where we end. There's a lot more to learn. Okay, so we're done with the course. There's one more homework where you're going to try and apply this by yourself, study for the test, and good luck.